Okay, good afternoon, all, and welcome to this live technical discussion related to concrete technology for structural engineers. So, as a structural engineers, we have many questions related to concrete technology because many times we might have to review the RMC report, and many times there may be a condition wherein site people may sign to the report for the approval, and at that time there are a number of questions which we received. So of course we had few discussions in the past, but again we feel that let's have this series getting continued, and then let's have more focused discussion on this topic. So Dr. Yogini Deshpande will join with us shortly. Okay. Yes, very good afternoon, Suresh ji. So right now this broadcast is live on LinkedIn, YouTube, and Facebook, and you all will be able to interact with us through the live chat. Okay. 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 So let us invite Dr. Yogini Deshpande in the live discussion. Hello. Yeah.
Hello.
Hello. Yeah. So very warm welcome to this unique live technical discussion related to concrete technology. Yeah.
Good afternoon and namaste to everybody, to all those who
Namaste.
have joined.
Yeah.
Very thankful, Mr. Bhavancha, for inviting me to this forum of yours. You've been consistently
Yeah.
delivering lectures and discussions,
Same
and
for
I've
me.
seen a few of those, and I'm delighted to be here today.
Yeah. Yeah, it's our pleasure to you have on the board today for a very important discussion related to concrete technology. So when we upload this event in the social media, many participants through registration form, they said that this is a very important topic and we want more such detailed discussions on this topic. Okay, so before we get into any technical discussion, can you please quickly tell us about your journey, like how you reached into the area of concrete technology, because you also did masters in geotechnical engineering, right, as I understand. Yeah.
Yes, so I did my bachelor's in civil engineering from Mumbai
Mhm.
University, and
Mhm.
I was enrolled for my master's in geotechnical engineering at Sardar Patel in
Mm.
Mumbai University itself.
Okay.
And this was around 99 or so. And that time, there was this push for developing high performance concrete.
Okay.
And I came to know that the Atomic Energy Regulatory Board was looking for research fellows for a team to be put together for developing high performance concrete for the nuclear power plants. And this was
Okay.
going to be done for the first time in India because there was not much knowledge about how to use Indian cements and Indian fly ash, or silica fume, which was imported, which still is imported from outside, and how to use that. What are the mixing aspects that need to be considered? What admixtures need to be considered? All
Yeah.
of these things. There were a lot of gray areas and a lack of knowledge in that. And so, Atomic Energy Regulatory Board, which is a part of the Ministry of Defense, put together a research project on this, and I was asked if I wanted to join, and I heartily agreed to it because it was something very new, upcoming, and I didn't think anybody would get this opportunity. So I grabbed it with both my and after that, then can you hear me?
Yeah. There was little bit lag on your side, so we couldn't understood your couple of last statement. Yeah. If you can just repeat it, please.
Okay. I'll repeat.
Yeah.
Just as the project was coming towards completion, I planned to do my PhD, and I had the opportunity to go to US. I got a scholarship at Purdue University to work in the materials department over there. And concrete is a very specific area in civil engineering, which is really
Right.
not looked into much as a research area. For a very long time,
Mm.
it wasn't. And there is a science to it. There's a material science behind it,
Yes.
which a lot
Yes.
of people refuse to understand or look at. It was more like, let's just take some cement, some aggregate water, and mix it and push it out. But the US has a few universities which specifically look at it as a material science and understanding of material science. So I got interested in concrete technology, was given a major thrust on from a learning and research perspective. And when I did my PhD,
Okay, there is some network issue, so just let's wait for a couple of
so
minutes
when
to
I
get
went to
it.
Purdue University, it really opened up my mind. Can you hear me now?
Yeah, now it's perfectly fine. Yeah, please go ahead.
Can you hear me now?
Yes, yes, yes,
Yeah.
yes.
Okay. So I changed my internet connection, so I think this should be
Okay,
better.
okay, great.
Uh, so at Purdue University, it was really an opening of the mind, because every material that is used in the construction industry, be it soil, be it aggregates, be it steel, cement, everything is looked at from a material science perspective, from the
Mhm.
microscopic study and analysis to a macro, and how it can be utilized in a better way, in a sustainable way in the industry. So
Right.
that was the journey. After that, I was in academia for a few years in the US. I taught at two
Mhm.
universities, and in
Mm.
2012, I decided to come back to India. I
Okay.
always did want to come back to India, and so since then, I've been working with Innova Consultants. We've majorly developed into assessment facilities for the construction industry, right from pre-rendering stages all the way up to demolition, and that is what our major consulting is into today.
Okay. Great, great. Okay, so let's initiate our talk related to concrete technology. So we received many interesting points through the registration form, right? And out of that, few of them you will be touch upon today, right?
Yes, I will, and I have kept some slides ready, sort of to
Yeah.
based on the questions that may come through the webinar to
Mm.
respond to. And actually, concrete technology is a very vast subject.
Yes.
So
Yes.
I'm going to talk, and then as we receive questions, we'll try and respond to them.
Definitely.
Or if anybody wants us, to go into a specific particular area, I can try and pull up from my slides if there are any related slides, and I'll pull them up on the screen and we can take a look at them.
Perfect. Yeah.
So this is just a current. This currently represent Renova Consultants. Like I mentioned, it's a consulting and infrastructure evaluation company for the construction industry, and do we do evaluations from a 360-degree perspective, right from pre-tendering stages to the demolition stages. This is a little bit about myself. I've talked about it right earlier, so I'm going to skip that a bit now. But I continue to be involved with the professional bodies. I'm a part of the repair committee at the American Concrete Institute. I'm part of the recycle concrete aggregate for Rylam. I'm on the board of directors for Enter Chapter of American Concrete Institute. And I recently joined OP Jindal University as a chair professor. I give some amount of my time over there in helping them develop their research at the civil engineering department. So to come to our main topic of today, concrete is one of the most used engineered materials in the world. So one might think that mobile phones might be the most engineered used material, but it's not. After water, which is a natural material, which is the most used material by human beings in the world, next is concrete, which is an engineered material. So as an engineered material, it's the most used material in the world. And so study of concrete and ensuring that we deliver a good quality concrete which has a long term performance to a client, to a user, is a very important aspect as a professional civil engineer. And it's a formidable rock. If you go to see, it is cemented together. It's a composite material of a binder and a filler, filler being the aggregates, binders being the cementitious material that we use in the for making it. Now, the uniqueness for us as civil engineers actually is that we are constantly moving between three scales. I know we design for a, let's say, a 100-meter building, but when we are designing it, it is based on the strength of a cube, which is 15 centimeters, and the cube strength is developed based on the micro and a nanoscale materials that are used to make the binder and to make the concrete in itself. So actually the beauty in what work we do, that we are constantly moving in between three scales, from a macro scale to the meso scale and a micro scale. And as civil engineers, we have to be aware of what is the effect of any defects that happen at a micro scale on a macro scale, or what may happen at a macro scale, what are the defects that happen on a micro scale. So what I mean to say is, if there are shrinkage cracks, these typically happen at a micro or a meso scale, but the effect is seen on the structure in a larger way, where there might be a structural failure because of inadvertent shrinkage cracks. The other way around, if we have a fire in a building, or any fire in a concrete structure, the structural failure happens because there is a large change in the micro this of what the concrete is, and there's a chemical changes that happen within the concrete during a high temperature fire, which causes structural failure, which may or may not be evident post the fire is curbed and everything. So there's this aspect of where we have to, as civil engineers, be conscious about what is happening at different scales and how each is affecting the failure aspect on a long term basis. So, for a very long time, till about early 2000, concrete was considered as a mixture of cement, water, fine aggregate, and coarse aggregate, and it was more like it's even today it's like a baking process. That if you have certain ingredients, we calculate how much amount they have to be, and we put it together, and sort of, just as we bake a cake, we would make concrete. In today, we are continually using mineral admixtures and chemical admixtures to ensure that the concrete is sustainable for a long-term performance. In the past 15 years or so, the usage of mineral admixtures in the form of fly ash, slag, and silica fume has increased extensively. Because of the usage of these mineral admixtures, we're having to use chemical admixtures. So all of these have changed how the concrete behaves, how it performs, and what we are able to derive from the concrete very extensively in the past 15 to 17 years. And as a concrete technologist, as a concrete user, what we need to understand is how each ingredient affects the behavior of the concrete, how we can utilize the best aspects of each of these ingredients to make the concrete sustainable, to make the concrete durable. So be it cement, be it water, fine aggregate, or the mineral admixtures. As a concrete technologist, I think it is very essential always to know what each ingredient is, what are the how it affects the quality of the concrete, how it affects the performance in the initial stages, during the manufacturing, during the processing, during the travel, during the placement of the concrete, as well as during the hardening stages. And if we are able to know, if we are able to understand these aspects, then we are able to harness these qualities for a good performance concrete. And if we are not able to understand what these aspects are or how they are interacting with each other, then it becomes difficult to harness the properties and to have a good performing concrete. And one of the major problems that occur at site is this lack of understanding, lack of knowledge that may be there, that does not allow us to harness the complete good aspects that can be raised from a particular material that we are using. So requirements of a good concrete typically are that it be mixed, transported, and compacted as efficiently as possible with minimum energy requirements. So your pumping requirements should be minimum. You don't want to have a higher amount of fuel to be utilized, higher amount of pump capacities to be utilized. You want to have good strength requirements in terms of compressive and flexural strength. You'll be able to fulfill durability requirements to resist the environment in which the structure is expected to serve. And while it is doing all of this, it has to be as economical as possible, so that we are able to ensure that for every paisa that we spend, we are able to get a long-term service from it. So that's what happens is, when we are making good concrete, it involves ensuring that we have good raw materials, we have proper proportioning of materials, mixing is being taken properly, transporting, placing, compaction, and curing. All these aspects are being maintained during the whole process. Now, there are certain weak links that are there in concrete. When you have to have a good quality concrete, we have to ensure that the water quantity is correct. Anything less or anything more affects the strength, affects the segregation properties. The aggregate quality is good. The gradation is correct. A very harsh mix results from aggregates that are where this aggregates are of only of a particular size in itself. There's not a smooth curve on gradation of the aggregates. The volume also impacts majorly on segregation and compaction abilities. It also impurities. If there is more clays or fines in the fine aggregates, it affects typically the ability to placement, as well as slump loss that happens at site because of these aspects. Admixtures, the major issue that happens with admixtures, one is the cement compatibility, but which I believe a lot of the cement, the admixture industry today has resolved extensively by ensuring that there is a proper technical salesperson at their end to ensure that for a given a cement, a proper admixture is given to the concrete supplier. Now, but the what major aspect that many times happens is the addition. What time do we add, and how much do we add? Do we add all of it at the beginning? Do we add half of it at the beginning and half of it during the transportation, or at the time of placement? There are some of these issues that happen at size. Now, the addition and the timing of it depends primarily on what is the duration for which the trucks are going to be transporting the concrete. If the duration is less, we could have an addition at the beginning itself, and you can have the whole addition at the beginning itself. But if the duration of time between the time that it leaves the RMC plant and it arrives at the site is more, you typically want to have a half and half kind of a thing, where you add half the admixture dosage in the beginning, and you add the rest of the half of it just a little bit before placement, or halfway through it is being transported. So this depends partially upon how much amount of cementitious material is being used in the mixture, and also what kind of admixture we are using. If we are using SNF based admixture or PCE polycarboxylate based admixture, this also decides what would be the amount of addition, as well as what would be the time of addition of the admixture. The placement and mixing, both of these make a major aspect on the quality of the concrete. So placement basically is deals with the aspect of pumping. If it is a high-rise building, pumping is a major issue. You have to ensure that the concrete remains in a good condition, a pumpable condition. There's no segregation happening, even while it is being pumped to 20 stories, 30 stories, and then being placed. The placement and the mixing is depending upon, again, the time of the day, the amount, the time it is going to be hauled from the RMC plant to the location of where it is going to be poured, and the temperature of the time. So all of these aspects are going to affect the placement and the mixing. And for this aspect, then we have to ensure that we are either using cooler water, ice, or icicles during the mixing, or try and not do the placement during the middle hour of the day, about between 12 to 4, and only doing it in early morning or later in the evening aspect kind of things. Now, coming to, like I mentioned in the beginning, understanding of the cementitious materials, or what materials are being used, be it cementitious materials or aggregates, what are their properties and how we are using it, how we can possibly use it, is a very necessary. Now, cement is with cement these days we use a lot of fly ash. We also use slag or silica fume. And what happens in this is that cement is a much coarser cementitious material in comparison to silica fume or even slag. Fly ash is a little bit along the similar lines to cement, but a little finer than cement at times. You do get the ultrafine fly ash, which is much more finer in terms of its particle size than cement. So when we are making a mixed design, understanding of how the packing density is going to be for the concrete mix design, because we are designing for a 1 cubic meter of concrete. And in this case, what we start off with doing is we have the larger size aggregate, then we have the smaller size aggregate, and then fine aggregates, followed by the cement. And the nano size particles that we want to have act as maybe as a filler, or as well as taking part in the chemical reaction and reacting with the calcium hydroxide in itself. All of this has to be noted and ensured, so when we are designing the mix. If we need a mix which is on a higher strength, maybe M60, M70, then we would typically have to go with cement, fly ash, and silica fume, or cement, slag, and silica fume. Some amount of silica fume may be needed, but again, based upon what is the haul time, what is the time of concreting, in terms of cost, what are the costs that are we ready to spend, if we would decide if we want to use silica fume or not. Because typically with silica fume, you would need to use expensive admixtures, chemical admixtures, as compared to what you would need to use with slag or fly ash. With fly ash, if you're using only cement and fly ash, typically chemical admixtures of SNF types can be used, and these are cheaper in cost as compared to PCE types. So, what happens when we use supplementary materials is that typically for fly ash, we are able to reduce the water demand to a certain extent. This helps us in the strength. This also helps us in the workability. Fly ash also helps us in the workability using fly ash. Even with slag, it's the same thing. We are able to reduce our water demand while increasing the workability. With silica fume, the water demand, because it is a much finer material, one of the most finest materials that is used in concrete today, is silica fume. And because of finer, because of the higher fineness, there is a larger water demand. And to counter this larger water demand, we then have to use better admixtures, chemical admixtures, which are slightly on the expensive side. The workability also is slightly reduced in case of silica fumes. It's a more stickier mix as compared to fly ash or the slag. Bleeding typically is always reduced for any when we use any of these cementitious admixtures. And they're one of the biggest positive aspects of using supplementary cementitious admixtures is the of being ability to reduce the amount of bleeding. Bleeding also tends, once we have controlled bleeding, we're also able to control the segregation of the concrete. Setting time, fly ash concretes tend to have slightly increased setting times, slag to some extent, but not necessarily always. Silica fume has no impact on the setting time. And the heat of hydration. One of the major, again, benefits of using supplementary cementitious materials is the reduced heat of hydration. A large amount of heat is generated when we use higher cement content. So anything beyond 450, 475 tends to have higher amount of heat of hydration being generated. And if you're pouring for large foundations or slab floor ground ground slab floorings and things like that, typically a larger amount of heat of hydration is generated. Again, if the sunnier days also add to the aspect that higher heat of hydration is generated, and this then tends to lead to early shrinkage cracks, early plastic shrinkage cracks. So you typically fly ash and slag will always help you to control the amount of shrinkage that can possibly happen in the concrete. So if you are having larger pores or larger size of elements, it's always helpful to use fly ash or slag in the mix. Early age strength gain are an important aspect for structural engineers because they want to start the next floor. They want to start the next stage of the structural elements as soon as possible. And typically, what happens is if you use only cement and fly ash, it tends to give you larger benefits in the long term strengths and the long term durability, but not in the early age strengths. And this can be countered by either using slag with fly ash or using a ternary mix of silica fume with fly ash or alkafines with fly ash. This will help in having early age strength gains compared to just using cement and fly ash. All the cementitious materials always benefit the long-term strength gain, and typically compared to controlled concretes for the same water to cement ratio, anywhere between 5 to 7% to about 30% in 30-35% increase of strength can be achieved. Permeability, water permeability, rapid chloride permeability, all the different types of permeability issues that we may have will get definitely reduced because supplementary cementitious materials react with the calcium hydroxide that is generated in the cement hydration process after about 2 or 3 days. And so once it starts reacting with it, the amount of pores that are developed in the concrete get reduced, and this helps in ensuring that you have a more impermeable structure as possible. Chloride ingress, like I mentioned, also gets reduced in the same format. The alkylic silicate reaction or alkali silicate reactivity, we don't come across this issue much in India except for the regions of Orissa, Chhattisgarh, Jharkhand to a certain extent, and some states in the northeast, Tripura, Mizoram, where there are certain kinds of slightly unstable compounds or elements that may be found in the aggregates. But typically, alkali silica reactivity, which happens about 5 to 7 years after concreting has been done, will get reduced when we use fly ash or slag together. Same thing with sulfate resistance also. Or all of the SCMs typically increase the sulfate resistance of the concrete. So what I'm trying to say through these 2 3 slides is that um, all of aspect of concrete making depends on us understanding what are the positive and the negative benefits of using the different materials that we can possibly use in concrete. And if we are able to understand and remember what each material brings to the table and how we are able to utilize it, then we are able to control the other issues that develop for us at site. Major issues that develop for us at site is always during the mixing and the placing aspect, or during the curing and the hydration hardening aspect. Typically, from the first 24 hours to 7 days, cracking issues happen. Yeah, early plastic shrinkage cracking happens, and all these aspects can be controlled by ensuring that we are utilizing proper materials, knowing which material is giving us what property, and then ensuring the quality of these materials that we're utilizing to have a good concrete. As I mentioned earlier, so major issues that we have is a truck arriving late at site, which is related to admixtures, chemical admixtures, temperature or improper mix design of concrete in itself, delayed curing, and shrinkage. Now, what I'd like to point about in terms of the improper mix design, what we have seen many a times is this. Many a times builders or contractors, they do not have an understanding of how the material variability happens. So we have cement is not the same cement. Ultratech cement is different, ACC cement is different, Ambuja cement is different. And not just as that each cement is different, but each batch of that within each company could also be different. In the similar way, the aggregates are also, each lot of aggregate is different. So when you send the materials for mixed design, you have to send the same materials that you are going to use to prepare the concrete. The same have to be sent for the mixed design, and the mixed design should be developed on that basis. And once you're able to do that, then you're able to control the quality this. So we have had many a times people, they want to use, they will a different cement for the mixed design purpose, because the cement has not arrived at site, or whatever different issues that they might be facing. What happens in this is that when we are using one type of material for the mixed design and one another type of material, the name may be same, it might still, aggregate it will be 20 itself. But if your source is changing, if the batch is changing, then the quality of that aggregate has changed. And sometimes there is a large major variability that happens between what was used for the mix design and what is being used during the mixing and the placement during the concreting stage itself. And this leads to a lot of issues. This leads to a lot of wastage of materials also. So if you are able to be quality conscious from the beginning, you will be able to save at least more than 5 to 10% during the concreting process itself, if certain basic aspects are being maintained right from the beginning, so that we are able to achieve a good mix while concreting itself. I will stop here for now and see if there are any questions. Mr. Bhavinsha, could we do that and then go back?
Yeah, sure. Let us take a few questions, and then again we can discuss it further.
Yeah.
Okay, one of the question was, there is also the fourth scale, which is the ultimate, as many literature suggests, that is nanoscale, on which the material property of concrete, that is CHS, gel, depends. Could you throw some light on this?
Okay. Let me see if I have this. Okay. Okay, so let's look at the basic first. The what happens in when you have water and cement reacting is a chemical reaction, and the reaction is exothermic. And what happens is C3S, the calcium silicate, reacts with the water to form calcium silicate hydrate and calcium hydroxide. And the calcium disilicate also reacts with water to form calcium silicate hydride and calcium hydroxide. Tricalcium aluminates in the same way form calcium aluminosilicates. Now, this, if you this is how it actually looks in the real microstructure. So this is a this is a this is at a nano level that you were asking about. And what we see in the microstructure typically is that this is the aggregate. And the calcium hydroxide tends to have a slightly more porous structure than calcium silicate hydrate, because calcium silicate hydrate, there's clearly three elements or three compounds in it, while calcium hydroxide is having only two of them. So calcium silicate hydrate has a larger tighter structure microscopically, and that is what ensures that the concrete will remain impermeable. Now, so in this, the gray area, the very solid gray area that you see, is typically the calcium silicate hydrate. And this more a mixture of black, gray, and white that you see over here in this portion is typically a mix, where you have the calcium hydroxide being formed, and some of the cement particles that have not hydrated. So let me just go back to one slide and explain to you how the cement hydration process happens. So when the cement comes into contact with water, what happens is there is a protective calcium silicate hydrate, that is formed around a cement particle. And this is where we are able to transport the concrete in this stage, because this protective barrier is ensuring there is no hydration occurring at during that time. It's just sitting quietly. There's a water layer all around that cement particle. Now, over a period of time, what happens is the calcium and OH ion, they start interacting, and the C3S starts hydrating. The hydrating process is very similar to eating a Halls. If you take a Halls and you or a menthol, you put it in your mouth, what do you see that happens? That over a period of time, the menthol starts reducing in your size in your mouth, and there is heat that is getting generated in your mouth, and all that liquid that gets formed in your mouth then cools your throat. It makes the throat better. So the cement hydration process is something very similar, that the hydrate product is forming all around that cement particle, and that chemical reaction is continuing, and that cement particle is continuing to get smaller in size, so that after 24 hours or after 36 hours, what we would have is that grown very small in size, and the hydration product has increased in size. And that is what you are actually seeing over here, that these white particles, small white things that you see, are actually the small cement particles that have left behind, and the grayer particles are the ones where the cement is fairly almost completely hydrated, or to either CSH or to CH. So more this is what the CSH looks like in a microstructure, and the CH is more platy like. The CSH is more amorphous, and doesn't necessarily have a very specific shape, but the calcium hydrate is more platy like, and this is how it looks like. And it looks like stacks of files or stacks of plates placed one after the other. And this is an initial mix of silica fume and cement and water, and you would see that a lot of CSH is formed and some amount of CH is formed. This is within about an hour's time of cement and silica fume being mixed together. And this, you see, is a much more denser, as you can clearly see. This is at about 7 days that I have, it's about, sorry, no, it's about 28 days with cement and silica fume. And you see such a dense thing that has formed, and just one plate of CH remaining, or one plate of, not unhydrated, but slightly more permeable aspect of the hydration product remaining, whereas a larger amount of CSH is being formed in case of silica fume concrete. So this is what happens, why we say that the permeability is reduced considerably when we use an SCM, is that the presence of CH gets reduced, the presence of any impermeability that might remain within the concrete gets reduced, because much of the CH gets converted to CSH, which is a far more denser product, and it has very, very less pores left behind for the water or chloride or any other gaseous ingress into it. This again is, a similar microstructure where you see an unhydrated cement paste, and CSH is getting formed around that hydration, around that cement particle, and slowly that hydration process will continue over a period of time, reducing that cement particle to a very small particle, which, as just one white dot maybe. So the one of the key things that you can sort of take away is that cement doesn't necessarily completely hydrate when we make when the concrete is hardened. Some amount of cement particles continue to remain in that unhydrated stage over a period of time, and that is what is being utilized or taken this when we have certain waterproofing chemicals that are used, or bacterial concrete that is being developed. That the idea is that the unhydrated cement or any of the CH that is formed will react once a crack has happened, and certain CSH will get formed at that point of time, and the crack will then close again. Any next question?
Yeah. Next is, can you please share your views on green concrete, or if the concrete material which is obtained while dismantling of building, can this be used to replace cement at some percentage and to increase the concrete strength?
Okay, great question. So green concrete, I'm not sure what you mean by green concrete. I'm assuming that green concrete, you mean to say that you're using some kind of waste material or this, and in which case, silica fume is a waste material, fly ash is a waste material, slag is a waste material. So we have sort of mastered the art of development of green concrete in that sense of things. Now, coming to your point of the demolished concrete, is it usable? Yes, very much. And actually, I've done a fair bit of research on using recycled concrete in concrete. This recycled, the concrete which is obtained from demolished structures can be utilized in the concrete in the form of aggregates. So it's called as recycled concrete aggregate, and this would depend upon what the initial concretes, what is the this how much deteriorated or distressed it is in terms of from a chemical perspective. That is, how much amount of carbonation has occurred in this concrete. If it's from a chemical industry, if it has had a lot of ingress of chlorides or any harmful other gaseous materials, then it may or may not be advisable to use this kind of concrete back into an RCC structure. But we could definitely utilize this such concrete as a recycled concrete aggregate for structures which are non-RCC, which could be maybe making paver blocks, or in the side pavements that might be required in a complex for where the building is being reconstructed, or any such thing. So elements which are not RC, which don't have a reinforcement in it, they could definitely be built. They could be manufactured by using recycled concrete aggregate. And recycled concrete aggregate, it is used very much in a very similar fashion like what we would use normal aggregates. Only thing is we would have to ensure that we're correctly calculating its density and its specific gravity also. But actually and definitely recycled concrete aggregates do increase the strength. They do increase the strength to a certain extent by about 5 to 7%, depending upon what is the initial unhydrated cement content that's left in that recycled concrete. Also, what it does definitely is that it increases the bond with the cement, within the concrete in itself. So the bond properties between aggregate and cement, cementitious materials, are definitely improved if we are using a recycled concrete aggregate.
Yeah, one more question. What to proceed as a point of quality steps during continuous mass pouring where the frequency of transit mixtures are not maintained by concerned contractor?
You mean to say quality in terms of the placement process, or the concrete that is placed already, or as the mixers are coming, so if I look consider from the as the mixers are coming in, what would need to be ensured is that the concrete is designed in such a way that the concrete that was poured initially would not get hardened or start setting before your last pour. That would have to be ensured, because otherwise obviously there'll be development of cold joints and some other issues, structural issues that will happen, because if one side of the concrete has started to set and the last before the last pour happens. So that can be an issue. And I think in such a case, you would have to have a discussion with the RMC supplier to ensure that certain kinds of admixtures are used, which will ensure that there is a delayed setting of the concrete. But delayed setting can sometimes affect your strength. So some amount of discussion or some amount of initial mock this should be done to ensure that you have a good the control over the strength and the setting aspects of it. What also could be done is to use maturity methods to see what is the strength development and the setting development that is happening over a period of time before the concreting is put into place.
Yes. So with this question, I was relooking into the points which we have received through registration form. So that was one of the common question, that how far it is advisable to add admixtures on the site.
Yeah, so like I mentioned, that's you can we can add admixture. Now if let's say we have done a mix design at during the mix design process, we have said that we would add about 1.1 or 1.2% of the cement content as the admixture. Now if there is a delayed pour for whatever reasons, about 0.25 to 0.5% of admixture could be added at site. But again, the mixing should be done properly, and then pouring should be done. Now admixture, addition of admixture does not necessarily affect the strength per se. The long term strength is not affected. What might get affected sometimes is the delayed setting. The setting may happen at a little delayed if an additional admixture dosing is done. So your initial strengths, if you are going for 24-hour strengths or 7-day strengths, because you want to again start your construction up above it or something like that, or load the structure, that might get affected a little bit. That you would have to do a bit of a Again, do a bit of a mock this beforehand, do two mix designs, one with delayed addition of admixture, and see if there is a change in the setting time or something like that. Or obviously, of course, you have now good maturity methods that can be adopted at site, so we utilize them, monitor at what point the concrete is setting and starting to harden, and
Mhm.
then ensure that the strengths are have a good confidence that the strengths have been achieved. So yeah, bottom line, can the admixture added to a certain amount? Yes, but you would have to have a discussion with the RMC or the admixture provider,
Mhm.
and have some amount of study done beforehand, rather than just taking a decision tomorrow morning that, okay, if the truck is late, I will add some admixture and go ahead and do the
Right.
concreting.
Yes. Okay. Question is, CH is to be reduced to form dense concrete aggregate. Is that so?
Um, yes, one of the easiest ways to ensure that you have an impermeable concrete is to ensure that you have lower amounts of calcium hydroxide in the hydrated cement paste. And that can be easily done by adding fly ash. So even if you're making M20, M30 grade of concrete and not a very high grade of concrete, I would always advocate to use some amount of fly ash, because the fly ash will gobble up the CH to form CSH, and it gives you a good long term performance of the concrete. So G+2, G+4, smaller buildings also, or smaller structures also, I would definitely advocate to use fly ash, and fly ash is fairly easily available. At times, even for the smaller contractors or smaller this, it's available freely also. If you go to the power plants, they do utilize it. So if that is something that is and easily accessible for you, and if you are and your work is of a smaller size, but you're still keen to do ensure that you're doing good work, then I always advocate adding some amount of fly ash to the concrete.
How to select the grade of concrete for the tall structures, as we know that M30 is minimum.
Okay, I think Mr. Bhavinsa could be able to respond to that better than me.
Yeah, of course
Because
it depends upon, yeah, right, so it depends upon the strength of the building what we require. So your so questions at your end will be that how to achieve high strength concrete when we talk about, let's say, M80 or beyond M80, then how to achieve those kind of high strength concrete.
okay, so high strength concretes are typically you're going to be able to achieve with silica fume or ternary based mixes. So ultra
Hmm.
high performance concretes are going to be ternary or even quaternary. When I say quaternary, it means that you are having cement, you're having fly ash, you're having silica fume, and maybe
Hmm.
alkofine. But alkofine and silica fume are fairly similar in their properties.
Yes.
So maybe slag or with it or some this. So because higher grades of concrete is not is essentially you're reducing the pores as much as possible, from the larger size pores that happen because of bleeding, that happen because of mixing issues and pouring issues, to smaller size pores which are through the calcium hydroxide, or nanopores that remain within the concrete microstructure. And so that can be achieved by ensuring that you have a proper mix design which is based on a packing density rule, and you have achieved as much as good packing density as
Right.
possible. And packing density is nothing but saying that I don't have that slide in front of me in this particular this, but if you're able to put four big balls in a box, you would have so much more larger empty spaces or open spaces.
Yes.
But if instead of those four balls we put 12 smaller balls, so four
Hmm.
football balls versus 12 season balls, would mean that there is the amount of open space or free space gets reduced. So as
Right.
we continue to use this kind of maxim to ensure a good mix design, then you are going to definitely get a good higher grades of concrete. Now,
Yes.
all the higher grades of concretes are also achieved by adding certain fibrillated steel fibers also in them. So, carbon fibers and steel fibers also add to the strength of the concrete and to the ductility of the concrete, which ensures that we're able to get high strength concretes.
Yes. Okay, so Suresh ji has asked the question in I think 3 4 lines. He is asking, how do I ensure that placed concrete is good enough? If the temperature is very high, should I use that concrete? Maturity measurement of concrete, why it is not being followed or made mandatory? And last line, some contractors do not allow fly ash, then how do I control temperature?
Okay. Um, Maturity methods, why they are not being followed or made mandatory? I think there is primarily lack of exposure and lack of knowledge. So that leads to a lack of confidence in the method. But I would definitely advocate to using maturity methods to measure the concrete strength in the initial first 7 days, and it's a very good tool for mass concreting, or even concreting same kind of elements over and over, kind of this, because that gives us a control over what, from a quality perspective, as well as the schedules, the future schedules, in the construction activity. To respond to you about why fly ash is not allowed, I'm not really very sure about that, as to why it is not allowed. I don't see any issue in it. In fact, today cement companies, are selling PPC in large volume, and there's about 22% of this replacement of cement by fly ash and the PPC cement that is sold. So I know that a few years back there was some issues and contracts were not allowing, but I think now it's become fairly common that fly ash is being allowed in places where they're not. Then I think you need to reach out to concrete technologists, where we could maybe explain to the client as to why it is beneficial to use fly ash.
Yes. Okay, so we talked about strength aspect, and I was just coming to this point, and I the same question is asked, that role of durability for mixed design of concrete for severe atmosphere and marine structures. So, what are the precautions which may be taken up to fulfill the durability parameters in such scenarios?
Excellent question. So, durability parameters should definitely be considered, especially for concretes which are going to be exposed to severe atmosphere and marine
Mm,
structures.
mm, mm.
And today we have far more advanced aspects and understanding of durability than what we had a few years back. So, in which, the IS 456 said, okay, if this is the exposure, then use this is the maximum water cement ratio that you can possibly use, or this kind of cement should be used. If it's a sulfate attack, then you have to use sulfate resistant cement. But I think we've advanced beyond that basic rules that we need to follow. Again, one is of course to use supplementary cementitious materials, and as I've explained that, that will help us into reducing the pores. The other thing is doing certain advanced testing, which includes chloride diffusion, and using risk assessment models to understand what should be the required cover for structures which are exposed to severe atmosphere or marine structures. So, by doing the durability studies, and then doing a risk analysis and developing models, and then developing the cover based on these models, the cover to the concrete based on these models, will help us to ensure that we are having a good concrete from a durability perspective. So the durability parameters that you would need, from a testing perspective, that you definitely need to consider is carbonation, chloride ingress. Chloride ingress, to calculate the chloride ingress in terms of not just the rapid chloride permeability, which is the resistance of the concrete to chloride ingress, but also to what is the depth of the chloride that can possibly occur over a long term period of time, and also the rate at which it can occur. So it could be water, the rate at what water can enter, or the rate at which chloride can enter. So these are slightly more advanced studies that should be adopted in terms of testing, as well as developing models, and then utilizing the risk models, and then utilizing them for designing the concrete.
Right. Okay, in continuation to our last point, Suresh is telling RDSO do not allow in pre-stressed sleeper manufacturing.
Okay, yeah. So pre-stress, what happens is that fly ash is no does not have the ability to give you initial strengths. So obviously in pre-stress you want initial strengths, and heating of concrete also does not necessarily help in a fly ash based concrete. So that is one of the main reasons why they are not probably allowing to use fly ash for pre-stress sleeper manufacturing, because as I mentioned in one of my earlier slides, that initial strength gain does not happen for fly ash. It's the long term strength gain which always happens in fly ash concrete, and which is beneficial to the user. But initial strength gain is not there, and probably because that is not there, RDSO is sort of saying, okay, you cannot use fly ash. We don't want to have these issues, and again have to deal with it if a contractor uses it.
Yeah, very interesting question coming up. That while designing high strength concrete, it is known that mix require less water. But if it is ordered from RMC plants, by the time it reaches the site, concrete becomes unworkable. Hence, it gets hardened. Can you suggest something in this regard?
Immediate answer, throw it away. You can't really do much about it. But so because you can't really, if you add more water, it's not it's going to reduce your strength. But also understand that probably the hydration process has already started. Like in one of the earlier slides I had shown, where there was a graph of first, second, third, fourth stage, and this hydration process that had happened. If you could go back to the
Yeah, I'll just put it up.
yeah, no.
Okay,
This, I think it was 25 or 26.
25. Okay, okay.
Little ahead. Yeah, this one. So the earlier one. It was correct. Go back.
This one?
This one or the
Just
before one also would. The before one will also do. Yeah, yeah. So so if you look at this slide, I'm unable to see at the bottom, but if you are able to read it, you would see that there are. I've said that there are there's stage one, stage two, stage three. Now stage two is the dormant period, where you're it is important period when the concrete is still in the dormant stage, and you're able to transport it, again remix it if necessary at site a little bit, and then pour it. So during that whole process, even as the concrete is moving, the hydration process is not taking place. But if it has been more than 4 hours, then the hydration process starts, and there is an accelerating stage, and the initial set begins. So now once the initial set has begun, to a certain extent, utilizing that concrete for placement purposes is going to create a havoc, especially if you're having to deal with high pressure pumps and pumping and all of that. Then it's going to get stuck within the pumps, and it creates a lot of issues. So there's really not much that you can do possibly, other than ensuring that the concrete is reaching on site before that, or then utilizing retarding admixtures between the 15 minutes to the 2 hour stage, if you're able to add a retarder, add some amount of retarder so that the setting does not begin for the concrete.
Yes. Okay. Which SCMs or SCM combinations has better service life or better durability?
Uh, there is no specific thumb rule per se, because see, what is it that you need to achieve, and what is it that we are agreeable to pay. Both these aspects sort of are going to govern it. Almost all SCMs are good from a durability perspective. Excuse me. So it's not that a certain combination will always work, or a certain combination may or may not work. But typically slag and fly ash works well, or silica fume and fly ash works well. Silica fume gives us the strength, fly ash gives us the workability, and then it's a win-win situation for us from a long-term perspective. A lot of people have this thing about silica fume concrete tends to have cracks or shrinkage cracks, and see that comes from aspects of curing, aspects of when the concrete was poured, what was the temperature at that point of that process, because silica fume concrete tends to be a little sticky, and it also has a higher water demand. So we can't say that one works well and the other work well. If you are able to ensure the quality aspects, then any combination is going to be good.
Yes. Okay, so can you give a quick tips like how to perform the QA/QC control on the site related to the concrete mix?
Okay, so on site, like I mentioned, when once we have the decision about what is the grade of the concrete, and typically, of
Mm,
course, that is made during the design stage and in the tendering stage in itself.
mm,
But
mm,
once with the consultants, this it is finalized. What is the mix design? What are the acceptable SCMs that can be used? Then ensure that you're doing a mix, you're developing a mix design with the RMC manufacturer. If you're doing it on your own at your own RMC plant, then you do it with the same materials that you're going to utilize in the during the placement process itself. So that's the first aspect. Second aspect is to sort of imagine what are the issues that might arise yeah, beforehand, and then work them into the mix design. So like I said, if there is a long haul, if there are temperature issues, have these discussions with the chemical admixture supplier to ensure that they tweak the admixture according to your requirements, and utilize that same admixture throughout during the concreting process. Ensure that you have a good quality aggregates that are available, specifically that they don't have very high fine content or any clay content, because that always affects the workability of the concrete. Any small higher amount of some amount of clay, even during just another hauling process, or when the aggregate is being taken off from the ground and poured into the mixer, many a times that process is not done properly. Some amount of dust or mud from the ground beneath gets picked up. So some of these things should be taken care of. During the concreting process, ensure that slump is being taken before the pour, and at the point of the pour, if possible, definitely. And then only you do the pumping process. Placement process done correctly. If it is not self-compacting concrete, ensure that proper vibration is being done throughout, and ensure that all the trucks arrive in time, and there are no trucks held up, because many a times what happens is that because the pumps are not in good condition, or because the some or the other issues, labor issues, the trucks get held up because of that. So the haul might be short, but the concreting process is not streamlined properly at site, so the trucks get held up. So typically try and not hold up a truck for more than half an hour to 45 minutes at most, and do the concreting, which I know is many times difficult. But if you try and do that, and then of course cubes, use good cubes. I mean, the cube form itself, many times I see at site that they're 5-6 years old, they're bulging from the sides. The length and the breadth is not of correct values, and so that definitely affects the strength. And sometimes you might be doing concreting properly, but because your cube molds are not of good quality, the cube strengths are not achieved, and the
Right.
concrete fails. So each of these small things also adds up, and actually it's just the devil lies in the detail kind of a thing happens, that if you ensure that the details are taken care of, the larger thing automatically gets taken care of.
Right. 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 Perfect. Okay. How do you see usage of UFFA?
I'm assuming that UFFA is ultrafine fly ash. Correct me if I'm wrong, Mr. Tripathi.
Okay. Meanwhile, we can take a few more points. Seeing this time of dormant period of transporting concrete, filling comes as concrete mixing and transporting vehicles shall be given priority in vehicle lanes as we give priority to ambulances.
Well, that is something that we'll have to take up with the traffic police, I think. Probably a good idea, very interesting idea,
Yes,
and that we should probably convey to the traffic police.
yes, yes. Okay, Mohan is telling good session going on. Revision of chapters and relearning of technology may have been diminished with the time. Okay, what are the factors which affects the strength of concrete? Like, for example, you are achieving 7 and 14 days strength, but concrete fails at 28 days. This happened at one of the site for a couple of different batches of cubes.
Okay. Um, Typically, I know, so there is no uh, IS 456 does not give any specified criteria for what is acceptable strengths for 7 and 14 days. What we say, okay, 7 days may pass ho gaya, 14 days may pass ho gaya, is something which is more of rule of thumb. So when we say that, oh, 7 day strength was achieved, we can't really say if it was achieved or not, because there is nothing to compare it with. Like how FCK is at 28 days only. There is no FCK at 7 days. There is no FCK at 14 days as per the codes. So this perception that it achieved 7 day strength and it achieved 14 day strength in itself is probably wrong, according to me, in that sense of things. Now obviously, because we have done so much of concreting and we've done so much of testing, we do have certain thumb rules in our mind that we, or in the industry, that we are utilizing. So if we have this confidence that 7 and 14 day strengths were good or acceptable strengths, as a consultant, if you think they were good, and it's something failed at 28 days, possibly, there are multiple reasons, but one could be that the cube was not cast well. Like I mentioned, I know it could be the casting, so the workmanship in itself was wrong, or maybe the curing was not done enough, or if it was not if the cube molds were incorrect, or maybe the machine itself might not have been properly placed, or may not have been so there are different kinds of these issues that can arise. Also, there is a lot of misunderstanding I see in terms of what is the how do you measure or the 28-day strength in itself. So IS 456 says that it has to be so you measure you break three cubes and you get the three values, and you take the average of the three. Now, once you get the average of the three, you need to go back and check the values. If there is any one value which is less than 15% of that average or more than 15% of that average, you discard that value, and then you take the two values only, whatever remaining two values are there, for determining the average. Now, in this also, there is, if you are doing your test through an enable accredited laboratory, and if obviously so there's a whole other this of discussion of how the laboratory should be, what are the QA/QC processes that should be maintained at the lab in it itself. So I'll sort of just cut short and say, if you're doing the testing at an enable accredited laboratory, then each machine and each operator, there's an aspect called as measurement of uncertainty that comes, because there is an operator variation that comes in, that comes from the machine itself as well as the operator, the human also. So all of these aspects go into deciding if a cube is going to be acceptable or not. So typically, if your design concrete was M30, and if it came to M27 or M28, some of these aspects should be considered before saying if something is acceptable or not acceptable. Obviously, of course, if an M30 comes to M20 or M22, then it's going to be up for arbitration, or whatever the contract is saying. But it's 5 or 10% here and there. Then all of these aspects have to be considered when you are defining if a cube is passing or failing.
Yes. Okay. Okay, Suresh ji is clarifying. Your understanding is correct for UFFA.
Yeah. Okay. Ultrafine fire ash. I think it's a good product. I mean, obviously, but it's slightly more expensive. So, and everyone is concerned about cost at the end of the day. But the thing is, of course, what may be extra cost of 5 rupees today could be a higher cost in the maintenance. So, you using UFFA is obviously beneficial and should be done.
What is non-overlapping as mentioned in IS 456 for accepting cube results?
Non-overlapping. I'm not sure what that
Yeah.
is. I mean, I'll have to
Yeah, so
see
we
the
can
IS.
so we can request Rajesh ji to if you can write down the entire para or clause here, then we may discuss it. Yeah.
Yeah, yeah.
Yeah. Okay, how the concrete mix with the steel fibers will be designed, and what is likely to be difference in properties of green concrete?
Okay. Concrete with steel fibers is designed based on what is it that we are uh, envisioning for the concrete to perform. Is it just reduction in plastic shrinkage cracks, or increased strength and reduced brittleness? Because with higher strengths, the concrete tends to be more brittle, and steel fibers are essentially helping us from that perspective. So the percentage of steel fibers that is, and which is appropriate to the amount of cement being used, so it's percentage of steel fibers as opposed to what is the content of cement is how it is used. It's sort of slightly based on trial and error and experience, so there's it could, and what type of is it fibrillated, is non-fibrillated, what this type of steel fiber it is. It'll be based on that. So there's no hard and fast rule. Anywhere between 2% to 5% or so could possibly be used. And what is it likely to be difference in properties of green concrete? See, usage of steel fibers obviously changes the workability of the concrete. and you have to have a very good QC control over the materials that you're using, and have done some kind of this before a mock trial before you start pouring the concrete mix, and multiple mixes and multiple times of the day, looking at the behavior, looking at the long term behavior. Very similar to what an actual mixing, placing, transportation, mixing, placing, all of that would happen on site. You will have to scale it to the lab this, and do it before you actually use it and pour it on this. Major issue is, of course, the workability, and then leading to the pumping aspect of it, because steel usage of steel fibers tends to create clumpiness in the concrete, and we have to ensure that the mixing is done properly, a proper mixer is utilized with proper evolutions, with proper mixing time, and all these aspects.
Use of fly ash is more common as pozzolana today, but do we see other pozzolana material like rice husk, metacholine is being used as a fly ash as an alternative?
Water, see, at the end of the day, I keep saying, going back, you see, it's for any contractor, for any owner, it's cost. And rice husk ash or metakaolin is more expensive than fly ash. So something that is cheaper and is of the same property, why would they want to use something which is more expensive? But of course, rice husk ash is cheaper within the area where there is abundance of it. But if you're looking to haul RHA from Kerala all the way to Kashmir or to Delhi, it might be expensive. So why would anybody want to be doing that? Now, metacryolin is a natural material. It's a naturally occurring material. It is not a waste material like RHA or fly ash or something like that. So, the I personally, just as being a very pro sustainability advocate, would probably not utilize it as much if I have the option to use fly ash versus metakaolin, because why not use something that's a waste material than using a natural material in making concrete. Also, rice husk gas in general, even if it's in abundance, if in Kerala also, even when it's in abundance, it is a little more expensive because the processing of RHA is expensive. It's again a heat intensive process, and it is expensive. So fly ash is where the heat intensive process already occurred, and it was anyway done for something else. So now you have the end product readily available that you can just use.
How much percentage of quality is compromised when water is added in transit mixture, and what are possible structural damages which could occur with the time or in near future?
Um, Very difficult answer. There's no given value that if you add 1 liter, how much amount of strength is going to be reduced. Because especially given that today the materials that we're utilizing for making concrete are so much varied and so much difference. Typical 1 liter of concrete, 1 liter of water is going to reduce your strength by about 2 to 3%, definitely. So, Anna, how much water are you adding? That's going to decide how much your quality is compromised. And so, obviously, that then goes on to so your structural damage, because your strength is reduced. So, there's a reduction in the structural strength.
Right. Okay. Rajesh has clarified it is a table number 11, which is talking about compressive strength compliance requirement. So if it
I'll
is
have to
possible,
look this up. I'll have to look this up. Maybe he can
Mhm.
email me or something, and
Sure,
I'll respond.
sure, sure. Okay. Omkar Shinde has asked that can you please explain cement manufacturing process?
You know, I could, but I think it's a long
Yeah,
discussion.
very long,
Plus, there
very
are a
long.
lot of, I'm sure, a lot of cement manufacturing people who have probably maybe have logged in, and it would be a major this to talk about cement processing, with them having logged in.
Yes. Ace Kurana is asking, how would GGBS be advantageous over fly ash apart from the cost?
GGBS gives a little more higher early strengths than fly ash. GGBS also in itself has cementing properties. So silica fume and silica fume, when it comes into contact with hot water, nothing happens. So silica fume as such is an inert material until it comes into contact with CH, and then that's where the reaction starts happening. So unlike cement, which the minute it comes into contact with water, some chemical reaction starts happening. Same
Mm,
thing with GGBS. A fly ash also, especially certain fly ashes, they're more like inert. They won't react. They won't. Nothing will happen if they come in contact with water, and only becoming like one, stiff, the dove kind of a thing. But GGBS, does have inherent cementitious properties or cementing properties, and so it will have a tendency to act like cement, get affected by humidity, as such. So there's some slight advantage, you could say, in that sense of things. Cost, I'm not sure. That's not very. There's not a huge difference between the cost.
what is the optimum entrained air for cryogenic concrete?
Well, that's not something I really know top of my head,
Yeah,
to respond to.
yeah, yeah. Okay. We know SF is a microsilica, but PSD of SF suggests that SF particles, which is 99 percentage below zero point 0.5 micrometer, are less than 100 nanometer. They can be treated as a nanoparticles.
Okay, so what is the question there?
Yeah, I'm also trying to understand what is his question.
I mean, yeah, see, some of these names and words are sort of the like the management. This every few years the name changes, but the this remains same. What we want to
Yeah.
achieve remains same.
Yes,
It's
yes,
just jargon.
yes, yes. Okay, so we have reached closer to 1.5 hour now.
Yeah.
And still, I could see the questions are popping up. Okay, but
Okay.
so so once this live stream will be ended, again recorded video will be published on YouTube,
Okay.
LinkedIn, and Facebook, and then we can again request all the participants to comment on the video, and if possible we can send detail to Dr. Yogini Deshpande separately.
So sure, I can respond if I that's possible for me.
Yeah, yeah. Okay, just one last question we can take before we close it. Should NDT for concrete structures should be mandatory in all types of structures for a good quality control?
Yes, definitely.
Hmm.
Of course, but at the same time, understand the purpose and the analysis aspect of it, which again I find a lot of the knowledge for it is lacking. But yes, it's a very good tool, and it is a good tool from a QA/QC perspective.
Yes, yes. Okay, so thank you all for the participation from your busy schedule during office hours. And we are very much thankful of Dr. Yogini Deshpande for sharing insight on this very important topic. And of course, as it was discussed, that it is very vast topic, so only few things were discussed. And I'm sure that you all will be having many questions. So you can start populating it when this video is published on a different media, right? So now we are closing this stream. Okay, so have a good day ahead. Okay, and thanks a
Thank you.
lot.
Thank you so much
Yeah,
for
thank you.
inviting me, Mr.
Yeah,
Bhavinsha. And it
yeah,
was a honor to be here and a very good sharing experience. Thank
yes,
you very
yes.
much.
Thank, most welcome. Yeah. Okay, so with this we are closing this session. Okay, And in the next session, we are going to talk about earthquake resistant design and detailing of steel structures. So you all may be aware that the draft code is published, and we had one of the session before a couple of weeks, and now we are planning again the session on the same with more details. So please keep in touch with us, and then if you have any questions related to or discussion points related to the draft code, then you can share the details in advance to us. So we will collect those details, and then we will again have a detailed discussion, because last date of comments is 23rd June. So before that, let's study the document, and then we can send our comments to the BIS. Okay, so everyone is now telling thank you.
Thank you.
Okay, so
Yeah,
thanks,
it was
thanks a lot. Thanks a lot for participation and raising very interesting questions, right?
yeah, yeah, definitely,
Okay.
definitely, definitely.
Okay, so with this, we are
Thank
closing
you.
this session now. Yeah, bye.
Bye.
Bye. Bye.